All right, this video is for calculus, infinite series. This will be the last video in the series, and this topic is usually the one that is considered most confusing by most students, and understandably so. There's a lot going on here. So if you watch this video and you're not sure, or maybe just in class you're still not sure, I think the examples in this video are really good at illustrating what's going on here. But sometimes you might need to watch it a couple times before it sinks in. So it's okay. Remember, it's a video. You can watch it as many times as you want. You can always pause sections and try problems and then go back and see the explanations that may help. So hopefully you'll find this helpful to understand this complicated topic. It's called Lagrange error for Taylor polynomials. Okay, remember how we said that if you have a Taylor polynomial that is approximating a function, it is perfectly matched at the centering value. But as you go further away, at some point the polynomial starts to diverge from the actual function it's representing. That difference is called an error, or sometimes a remainder, and it's related to the idea that we saw with infinite series. Remember, we said that there is a way to calculate the error with an alternating series. If you go far enough out in the terms and the alternating series is converging, you can get as close as you wish to the actual sum. You get closer to the actual sum the more terms you include in the partial sum, and the difference between the actual sum and your approximation is called the remainder, and it represents how much error there is in your approximation. So with an alternating series, in the first half of this unit, we said the remainder is the difference between the actual sum and the sum of n truncated terms, or the nth partial sum. And then the theorem was that the error, or the remainder, is always less than or equal to the value of the first neglected term. Right? So it's not going to be exactly that, but that's the upper bound on the error. So the error will not be larger than the first term that you don't include. Right? And this is because converging alternating series, you have to have decreasing terms. So the next term is going to be the biggest term that you'll encounter in the rest of the series. All right. So something similar happens with Taylor polynomials, right? So we have the idea that the alternating series remainder is less than the first neglected term, the first one that you don't include in your truncated series. For the Taylor polynomial, the error, or the remainder, depends on two things. It depends on how many terms are included, so it's going to have the same idea that it's based on the first neglected term, but it also depends on which x value you're evaluating at, because the error is 0 at the centering value, and no matter how many terms you include, the further away you go from that, the larger the error is. So there's two things that it depends on: how far away the x is from the centering value, and also how many terms are included. Okay, so like the alternating series remainder, the Taylor polynomial remainder is still determined by the first neglected term, but now the expression for calculating that depends on the general form of that term, which is that derivative divided by that n factorial, and then times x minus c to that nth power. Right? So all those things play into the error. Now, the result of that is that what we call, in this case, the error is given a specific name. It's called the Lagrange error, or the Lagrange remainder. It is less than the value of the first neglected term, the absolute value. So the absolute value of the error is less than the absolute value of the first term that you don't include in your truncated Taylor polynomial. So if you have a Taylor series, you truncate it to make a Taylor polynomial. The first term you don't include determines the error. Right, and that is an upper bound. It doesn't mean the actual error is that. It means the error will not go above that. Right, but there's some complexities in this. Right, for one, this error goes up the farther this x is away from this c value. And the other thing, it depends on evaluating a derivative, which the derivative's value is different for all different x values. So when we evaluate the derivative for evaluating the, if you had the third derivative over 3 factorial over this to the third power, you have to evaluate it at a value. And that value we call z. And that z is whatever x value we can plug in between the centering value and the x value we're evaluating the function at. That will produce the maximum value for this derivative. Now that's complicated to kind of explain in words, but it's a little easier to see when we take examples. So we're going to build up with a series of examples, starting with alternating series and then transitioning over here and see how these things are related. Okay, so first, we're not going to do a series like from the second half. We're going to go back to the first half of the unit here where we didn't have x's. We were just talking about infinite series. Here is an alternating series, and we want to first just say for this series, this alternating series, approximate the sum of the series by using the first 6 terms. Okay, so all we would do in that case for part A is we would write out the first 6 terms of this series. So if I plug a 1 in here, I have a negative 1 to the 2 power, which is positive 1 over 1 factorial. So the first term here is 1 over 1. Right, this is an alternating series, so the next one is negative 1 over 2 factorial, and then plus 1 over 3 factorial, minus 1 over 4 factorial, plus 1 over 5 factorial, minus 1 over 6 factorial. And if you plug all this in a calculator and say math to fractions, that ends up becoming 91 over 144, which turns out to be in decimal 0.631944, and then the 4 start repeating. Okay, so this is an approximation of that series, right? We've written, if you wrote an infinite series out and added it up, it would be exactly what this series is. But since we're truncating at 6 terms, this is the approximate sum, the 6th partial sum. Okay, then it says for part B, find an upper bound for the remainder. Okay, so in this case, we can say this. The error, or the remainder, is less than or equal to the first neglected term. And I would actually write that, even on the AP test, if I was answering this, which is equal to, let's see, the next term will be, it'll be the absolute value of 1 over 7 factorial, or just 1 over 7 factorial, which is 1.984 times 10 to the negative 4th, or 0.00019884. So this sum is different from the actual sum by no more than this amount. Okay, and then they may say, all right, find the upper and lower bounds for the actual sum. So that means that the sum, right, is going to be somewhere between the approximation with 6 terms minus the error, the error, right, and the partial sum with 6 terms plus the error. Right, so we know that the real value is this value minus this, or this value plus this. So it's just well, let me write it this way. I'm going to use, this is 91 over 144 minus this error of 1 over 7 factorial. So the actual sum is somewhere between that and 91 over 144. Is it 144? Yeah. Plus this error of 1 over 7 factorial. In decimal, that means that these values are between, if you take this minus this number, you get 0.6317460317, and the upper bound is 0.6321428571. All right, so we haven't worked with anything with a function yet, but just reminding ourselves about something we learned in the first half, that you can just take the first neglected term, and if you take an approximation, it's within plus or minus, the actual sum is within plus or minus that amount. Okay, second example. Here's another one with just a series, infinite series. We're not connecting to a function. It's an alternating series. This one says approximate the sum of the series with an error less than 0.001. All right, so what we could do is write out some terms. The sum is going to be equal to, let's see, if I start with a 0 here, this is positive, so this is 1 over 0 factorial, so the first term would be 1 over 1. Second term will be negative, 1 over 2 factorial. Third term will be positive, 1 over 3 factorial. And then minus 1 over 4 factorial, plus 1 over 5 factorial. Wait a second, is that right? Nope, sorry, I'm making a mistake there. Let me go back. Getting ahead of myself here. First term is 1, but when I go up to 1, this is negative 1 over 1, and here makes this 2 factorial. right? But when I go up to 2 here, this is squared, so that's positive. This is 1 over 2 times 2 is 4 factorial, actually. So the third term is 4 factorial. Then the next term is 6 factorial. The next term is 8 factorial. And if we want the actual sum, we would continue with all the terms here. So minus, plus. Okay. So an infinite series would be equal to the sum. All right, so to determine where I can chop this off, I'm going to actually go back and figure out what these are in decimal. So if I write what these are in decimal, this is 1. This number is 0.5. This number is 0.2. Let's see, 1 over 4 factorial is 0.0417. 1 over 6 factorial is 0.000138. 1 over 8 factorial is 2.88 times 10 to the negative fifth, which is 0.0000248. Okay, so now if our goal is to have an error less than 0.001, let's see, 1, sorry, I think I had one extra 0 on this one. This is 0.00138. So this one is not yet below the goal. 0.0013 is not below 0.001. But 0.0000248 is less than 0.001, so we've met the goal. And that means this can be the first neglected term, because the error, if we truncate here, so if we truncate here, right, then that means the error will be less than this. So we're going to truncate here, which means we're just going to use this as the approximation. 1 minus 1 over 2 factorial plus 1 over 4 factorial minus 1 over 6 factorial, which if you plug it into a calculator ends up being 389 over 720, or in decimal, it's 0.5054027 repeats. All right, so that's an approximation. We have to go up to the 1, 2, 3, 4th term in this series. Okay, now it asks a weird question. It says, which memorized power series from the second half of the unit seems to match this form? All right, for that, I'm looking at this and thinking this has got a 1 over 2 to the n. The form from the power series list that matches that most closely is the cosine. Actually, the cosine of x is this series, n equals 0 to infinity of negative 1 to the n of x to the 2n over 2n factorial. Okay, so just as a way to get what the actual sum is, if we're talking about this series, which let me copy it down here, n equals 0 to infinity negative 1 to the n 1 over 2n factorial, matches this series. This matches, this matches, this matches, and this will match as long as this x is 1. You agree with that? So this is a match if x is 1. And that means that if this series is the same as this series was x is 1, you can just say that this series is equal to n equals 0 to infinity negative 1 to the n of x to the 2n over 2n factorial is equal to this function cosine with 1 plugged in. And so if I plug 1 into that function, I get 0.54030. So this is the actual sum. And this right here is a partial sum. This is a partial sum. And so this is not the real sum. This is something from a truncated series. But the actual sum, if we continued it out, we could use its functional representation to find that it's actually 0.5403. And there's a difference between these two numbers, and that difference is an error. Okay. So far, we're mainly working with functions. We're just starting to cross over to working with functions. Let's go to another example. Third example. Estimate e squared, which is just a single number. It's the e function, e to the x function with 2 plugged in, using a Lagrange polynomial of degree 10. All right? So let's start with that. For part A, we're going to use our memorized form rather than do the whole Taylor procedure here. We know that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial all the way up to, in this case, x to the 10 over 10 factorial, because we're doing a polynomial. So we're approximating now. This is the 10th degree polynomial for that. So this is approximately equal now. All right, so if we're going to estimate that, we have to plug. So if we want to evaluate e squared, then we have to plug in 2 into that polynomial. So that's 1 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial, all the way up to 2 to the 10th over 10 factorial. Okay, now I could do that and plug all those things in, but I think what I'm going to do is I'm just going to figure out the corresponding series that goes with that in summation form. So the finite series for that is, this rule is x to the n over n factorial, and I'm specifically going from 0 up to 10. Would you agree with that? That's this finite sum. Yeah, and I think I'm going to use that in order to evaluate this. If I just want to go to 10, yeah, 0 will produce, let's see, does that reproduce this? X to the 0 is 1 over 0 factorial is 1. That gives me a 1. For the n equals 1 case, that's x to the first power over 1, which is x. Yep, sure enough. All right, so I'm going to do that, but I'm going to plug in 2 for this x. All right, so instead, I'm going to take the summation from n equals 0 to 10 with a 2 plugged in there. Okay, and I'm going to use my calculator summation to do that rather than type it all in. Let's do that this way. You could do math summation. I'll use the variable key, so it's going to look like x equals 0 to 10. And then it's going to be 2 to the x in this case, divided by x to the, and then the factorial is in the probability menu under math. So that should give me that sum quickly, and it is 7 point, so I'll copy it down here. It's 7.388994709. And so therefore that is what the this approximate value is. So E2 is approximately the Taylor polynomial 10th degree with 2 plugged in, which is 7.388994709. Okay, so here's an approximation for e squared just using the 10th degree polynomial for e to the x. Okay, the second part of the problem says use the Lagrange form of the remainder to find the upper bound of the error. Okay, so for that, I'm going to write this, and here's where we're going to get to something that's really new. Okay, the Lagrange form of the error says that, similar to alternating series, the absolute value of the error is less than or equal to the first neglected term. But that first neglected term is the n plus 1th derivative evaluated at some value which we call z over n plus 1 factorial, and then x minus c to the n plus 1 power. This is the rule for the Lagrange error. Now let's evaluate what the different values are here. In our case here, n is 10, right? So this is going to be 11, that's going to be 11, that's going to be 11. The centering value is 0 because we used a Maclaurin polynomial. And the x value we're talking about is, well, let's see, it's going to be, we're actually plugging in a 2, right? So that's the x value, right? So I'm going to plug those things into the Lagrange remainder formula, right? The absolute value of the error is less than or equal to the 11th derivative of some value, which we don't know, over 11 factorial. And then this is going to be 2 minus the centering value of 0 to the 11th power. Okay, so for me to finish this calculation, I need to know what z is. All right, so that means we have to take the function f, which in this case is e to the x, and find the 11th derivative of it. So the first derivative is e to the x, The second derivative is e to the x. Luckily, all the derivatives are e to the x. So the 11th derivative is still e to the x. Okay, so now we can finally explain what this z is. All right, I'm going to make a plot of the 11th derivative. The 11th derivative of x, which is e to the x, looks like this. It's an e to the x function versus x. Okay, so the interval of interest is the centering value, which in this case is 0. We actually use a different color. The centering value, which is 0. And where we are using this is we're evaluating this at x is 2, so that's the x value. This interval here is called the interval of interest, okay? And we are trying to figure out which z value inside that interval will produce the maximum value for this derivative, okay? So the z is chosen to be somewhere between the centering value and the value you're evaluating the series at, which is this case 2. And you have to choose the value that will give you the largest value for the derivative. So since this derivative is increasing, this derivative is largest at this end of that interval. And that means this z value has to be the 2. We have to plug a 2 in. All right, so that means that we are going to plug a 2 in to this derivative. Okay, so now let me write this one more way. The absolute value of the error is less than or equal to now the function itself is e, so this will be e with that z value of 2 plugged in, okay, over 11 factorial, 2 minus 0 to the 11th power, and now I can evaluate that. In the calculator, this turns out to be equal to 3.791 times 10 to the negative 4th, or 0.003791. So this is the upper bound on the error. Right? This approximation here of e squared is no more than this amount off from the actual value of e squared. Okay. So that's how to handle this z. You actually have to figure out what the derivative curve shape is. You have to consider the interval between the centering value and the value of x you're plugging in, and choose z to be the value that produces the maximum value of the derivative, and use that for this derivative here. All right, last question in this one, what is the actual error? Okay, so the actual error, which would just be the function value at x minus the polynomial approximation at x, that's easy to find. Right? In this case, the actual error, this is the upper bound of the error. The actual error, which is the magnitude of f at 2 minus the polynomial at 2, is f of 2 is literally e squared. And the polynomial is this 7.388994709 number, right? So we can find that in a calculator directly. I can just say, take our calculator, take e squared, and plug in the function into the actual function, and then subtract this approximation that we got from before, this number. Just go on the calculator. And the actual error is, the actual error is 6.3159. Is that what I'm getting there? 6.1389. So sorry, 6.1389 times 10 to the negative 5th times 10 to the negative 5th, which is 0.0000614 approximately. Okay, so the upper bound on the error was 0.0003, but the actual error was 0.00006, was actually less than that. So this is a great example to illustrate that what the Lagrange error gives you is like the maximum value that the error can be. The actual error is usually less than that. Okay. All right, let's do a few more examples so you can see additional things on this. So this question actually comes right from AP Classroom. It's very similar to the way things are asked on the AP exam. We'll take a look at that at the end on the actual AP exam question. If if the fifth derivative of some function f is given by the function 700 sine of x, and if x is 0.7, so that's the value we want to evaluate at, and it's in the convergence interval for a power series that's centered at x is 0, find an upper limit for the error when the fourth degree Taylor polynomial is used to approximate f of 0. And they don't even give me the function, so I can't actually produce the Taylor polynomial. Okay, so how can we do this? Well, we could start by saying that we're being asked to find an upper limit for the error with the Taylor polynomial, which means that we can write that the absolute value of this error is less than the Lagrange expression for the first neglected term. That's going to be the n plus 1th derivative evaluated at that z over the n plus 1 factorial x minus the centering value to the n plus 1 power, if we include n terms. Okay, then I like to write that out, and then I like to try to find what all these letters are. The centering value here is 0. The x value that we're evaluating at is 0.7. 0.7. That's 0.7. And then the n is going to be the degree of the polynomial we're using. We're using a fourth degree polynomial, so n is 4. All right, so that means that I can fill this in now. This is going to be, if this is 4, then this is the fifth derivative at z over 5 factorial, 0.7 minus 0 to the 5th power. And then I have to work on this. What's the maximum value? I need the maximum value of the fifth derivative at z in the interval of interest. Okay, so they told me that if I were to graph this function, that they told me that this fifth derivative function is 700 sine of x, right? So a sine function looks like this, right? So this would be up to 700 here, right? Let's see, this is 2 pi, so this is pi here, so this is pi over 2 is where this is. Okay, so where is the interval of interest? Well, the centering value is 0, and we're plugging in 0.7. Okay, pi is 3.14, half of that's about 1.57, so 0.7 is maybe here, okay? And that means since this is increasing, this is going to be maximum right here, which means the z value is the right side of this interval, 0.7. So when we evaluate this function, we're going to evaluate it at 0.7. So the maximum for f fifth derivative at z, we're going to say is the fifth derivative at 0.7. And since they gave me a function for that, it is 700 times the sine of x. It's 700 times the sine of 0.7. Right? We can plug that in a calculator, but I'm just going to plug it in here. So here I've got this max error. The upper bound, upper limit is 700 times the sine of 0.7, and then divided by 5 factorial, 5 factorial, and this is 0.7 minus the centering value to the 5th, and that means it's less than or equal to, in this case, it's 0.631596. And at this point, we could truncate that to our usual 3 decimal places, 0.61632. All right, so that's how we would do this problem. Hopefully, as you're seeing this, you can start to see the meaning of z, the meaning of the nth derivative. We're still dealing with the first neglected term. It's just got more complexity to it. Okay, one more kind of basic example, and then, yeah, this one's more complicated. And then we'll do an actual AP question to finish off this video. Okay, if the sixth derivative of x is a positive decreasing function, actually there's 2 more questions, 3 more questions after, 2 more after this one. Find the error bound when a 5th degree Taylor polynomial centered at x is 4 is used to approximate this, assume the series converges at that value. Okay, this is actually the same kind of problem as the one we just did, so nothing dramatically different. Let me go through this. In fact, I think if you were to pause the video, you should be able to do this one based on the one we just did. So the absolute value of the error is going to be the n plus 1 derivative at z over n plus 1 factorial, x minus the centering value to the n plus 1 power. Okay, so what are the values we've got here? The centering value is 4. They said centered at 4. The x value in this case is 4.1, because that's what we're approximating. And the polynomial is a 5th degree polynomial, so n is 5. Right, so that means we can start writing this. This is 1 over, let's see, if n is 5, this is 6 factorial now. This is 4.1 minus 4 to the 6th power. And for this, we need to have the max for the 6th derivative at z, which means that they told me that this, if we were to plot the 6th derivative, it said it's a positive but decreasing function. So the values are positive, but they're decreasing. All right, and so where are we? We're evaluating, we're centering at 4. We're evaluating at 4.1. So if this is a decreasing function, that means this will be maximum at the left edge. So the z is going to be this 4 here. This is the z. So for the maximum of that, we're going to say it's the max of that is evaluated at 4. All right. So what we could say is we could just fill in that this is going to be f, the 6th derivative at 4, right? But we have no way to evaluate it further than that. So the answer is that the absolute value of the error bound is given by this expression. We can't go further because we have no way to find numerically what this number is, but we can write the expression out for it. Okay, so that's good. So now we're going to look at an example that I took from AP Classroom. So this is a College Board style example. And this also is a good illustration of terminology. The Taylor series for natural log of x centered at x is 1 is, and they give it in its summation form. Let f be the function given by the sum of the first 3 non-zero terms of the series. The maximum value of the limit here for this is what? Okay, so we might try different things here. This is a Taylor series, so I'm going to show you actually 2 wrong ways to solve it, and then we'll look at the right way to solve it. So what we might first do is say, hey, wait a second, this is a Taylor series, so why don't we use a Lagrange error? So Lagrange error says that the absolute value of the error is less than or equal to the n plus 1 derivative evaluated at z over n plus 1 factorial times x minus c to the n plus 1, and we can figure out what these values are. So let's see, the centering value here is 1. The x value we're interested in is what? Well, they didn't give it to us. So it means it's some value between 0.3, so it's a range of values from there to 1.7. That complicates things. And then it says now that this is the first 3 non-zero terms of the series. So I think we have to write these terms out and see what the degree is. So if I start with a 1 here, this is going to be 1 squared, so that is 1, so positive. And then this is going to be x minus 1 to the first power, so it's x minus 1 over 1. Right? That's the first series. That means the second term is going to be negative, so that's a negative x minus 1 squared over 2 plus x minus 1 squared or cubed over 3. So this is a 3rd degree, so this will be a n equals 3 polynomial here. All right, so we could go ahead and figure out what this is. Let's start writing some things in here. This error is less than or equal to, this is what's going to be 4 factorial. This is, I don't know what this value is yet, minus the centering value of 1, okay, to the, let's see, this is 4 power. And now for this, I'm going to have to evaluate the next derivative. So we're going to have to take all the derivatives. They said the function was natural log. So if f of x is natural log, then the first derivative of that would be 1 over x, or x to the negative 1, right? The second derivative would be negative x to the negative 2. The third derivative would be positive 2x to the negative 3. And then since we have to get the next one, we have to go up to the fourth derivative. The fourth derivative would be negative 6x to the negative 4, or negative 6 over x to the fourth, right? All right. So then I could graph this function, right? If we graphed the fourth derivative versus x, that graph looks like this. I'm not going to use a lot of time showing this in a calculator, but you can just use a calculator to graph it. So what is the interval of interest? Well, it looks like the x can be anywhere from 0.3 to 1.7, and the centering value is 1. So the centering value is 1. That's actually out here somewhere, okay? And if you go from, let's see, 0.3 to 0.7, it's there, right? So in this interval from here, and I mean, you could consider, yeah, they're saying over this range, I'm sorry, 1.7. Let me erase that. I need to go a little further here. Okay. So 1.7, this would be 0.3. 1.7 would be out here, right? We would have to figure out where the max is. Right? So I think we're going to actually have to graph this in the calculator so we can see that. Let's graph the function for the nth derivative. Right, so this would be, let's see, negative 6 divided by x to the fourth power. I'm going to graph that, and then I'm going to zoom in a bit because we're really only interested from about 0 to 2. So let's do that. Let's go from 0 to 2 in the x and a lot closer in the y, like negative 4 to positive 2 or something like that. Okay, so here is the graph of the fourth derivative. Yeah, I guess I need to go quite a bit further down in the y. Let's go like negative 20. I can see that. Okay. I think it's probably still not big enough, but now we're going to take any value between 0.3 and 1.7, and since the centering value 1 is included in that, this is all the interval of interest. Would you agree that the largest value, since I'm talking about taking an absolute value, would be on this left end, this 0.3? So I think we could go through all of that to determine that 0.3 is the lower bound. So 0.3 is the lower bound. That means we're going to use that for that because this error is getting very large as we go down here. So I'm going to evaluate that. For this error, I'm going to take negative 6 over 0.3 to the fourth power, and that is the value of the derivative I need. Okay, if you evaluate this in a calculator, you end up getting 7.41049. And this is a multiple choice question, and we look and see none of those match. Okay, so this was the wrong approach. Okay, so it's definitely the wrong approach. Let's take a look at another one. So it was wrong to look at this and say Taylor series because, yeah, there's just this just didn't work. Okay, another thing we could try is this is actually an alternating series. Right? We could try an alternating series error. So if we wrote out those terms, let me write them out again. This is a little faster than the previous one. We're still doing, I'd say, an incorrect approach, but let's say if we wrote the series, it's approximately equal to, the first term is 1, and this is x minus 1 to the first power, and then we've got minus x minus 1 squared over 2, plus x minus 1 cubed over 3, okay, minus x minus 1 to the fourth over 4, plus x minus 1 to the fifth over 5, right? But if we're stopping after the first 3 non-zero terms, right, then that means this is the first neglected term. So that means the error bound, since we're considering this to be an alternating series, should be the absolute value of negative x minus 1 to the fourth over 4. And we should be able to plug in some value for x. They say the value for x is this. So let's just actually look at this, this value. If I plug that into a calculator, I can graph that. So let's graph that directly as the error, as the upper bound for the error. So if I plug in negative x minus 1 to the fourth power divided by 4 and graph that in this region, I think I need to reset my window a bit. So let's say we go from negative 20 to 20. That turns out to be, what is it? Actually quite small. So let me zoom in quite a bit here, like negative 0.1 to positive 0.1. See if we can see the graph. There it is. All right, so looking at that, looks like the error, it depends on the x value, and they want the maximum value. So let me specifically limit this window now to 0.3 to 1.7. And then I'm just going to look at the graph and see if I can see where it's largest. Okay, it looks like it's the same on either end. So what I could do is maybe put a trace on here. Actually, let's do second trace and specify a value and plug in 0.3. That gives me negative 0.06020025, which is not one of my answers. And if I did the upper bound value, 1.7 here, at the upper end of the interval, I get the same thing. So unfortunately, considering this an alternating series does not give me any of the answers. So that one didn't work as well. Okay, so here's the problem. So far in analyzing this, we've been looking at the fact that that's a Taylor series, which made us think that this was Lagrange. Or looking at the form of this, which was alternating series, and saying we could do alternating series. We haven't been focusing on this, right? But here's the difference, okay? They actually asked for this, and this is simply the actual error, right? It's not the upper bound of the error. They didn't say upper bound of the error. They said actual error. So what we really need to do is figure out what this absolute value of this error is. So we actually can write out two things here. We can write out what natural log of x is. We already know what that is. It's a function, right? But the function, f of x, is the sum of the first three terms. So I'm going to now rewrite out the terms in the series again. This is going to be x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3. That is the function. And that means that this right here, this absolute value of natural log of x, I can just substitute this right in for that. Minus x minus 1 squared over 2 plus x minus 1 cubed over 3. This is the correct way to do the problem. And if I just plug this in a calculator and directly graph it, I'm graphing the actual error between the real function and the polynomial. So this is the proper way to do the problem, since they're asking about the actual error. All right, so I'm going to go back here and enter that. Natural log of x, so the true function itself, minus our approximation. So in parentheses, I'm going to put x minus 1, so parentheses x minus 1, and then minus x minus 1 squared divided by 2, and then plus x minus 1 cubed divided by 3. Oops, delete, down off the line. Divided by 3. Okay, if I plug that in and I evaluate that from x is 0.3 to 1.6, 1.7, now I'm actually graphing the difference between the real function and the approximation. And I can see from this graph that it actually is largest this difference is largest. Doesn't matter if it's positive or negative, because we're taking the absolute value at the left end. So if I go second trace and a value, and I force this to be right at 0.3, the value is negative 1.4456, which would round to negative 1.45, and that is the correct answer. The correct answer is C, 1.45. So I know we went through a lot of gyrations there. I wanted to show why the common ways for people to think to do this problem are incorrect. And we instead want to focus on the fact that this is the actual error and just graph the difference between the function and the difference and our approximate function. Okay, in the lesson notes, we have one last example. In this part of the lesson, we usually now are going to work an actual problem from the AP from the 2011 AP free response, the actual AP exam question. But since this video is already pretty long, I'm going to put that in another video. Hopefully by rewatching that first part, if you need to rewatch this video, that should help you solidify things. We'll come back in a separate video to do this last question.